And let me introduce our next and final speaker before break. And that's Henry Burns from Georgia Tech. Are you with us, Henry?
Hi, yes, I am. Can you hear me?
Yes, we can hear you just fine, Henry. So you're going to tell us about Avlis, right?
Yes. So let me get that
That's
going.
a fascinating technology, and we're anxious to learn more about it. So we'll turn the floor over to you, and remember to use your pointer. It's all yours, Henry. In 20 minutes, I'm going to interrupt you.
Okay, thank you very much. So my name is Henry Burns. I am a student at Georgia Tech. My advisor is Dr. Stephen Migalski, and today I will be talking about the isotopic composition of uranium enriched by Avlis. Oh, excuse me, sorry for 1 sec. This is getting in my way. So Avlis stands for Atomic Vapor Laser Isotope Separation, and it is a method of enriching many different elements, but today I'll be specifically focusing on Avlis used to enrich uranium. So Avlis works by vaporizing natural uranium and passing a tuned laser through the vapor, which selectively ionizes the uranium-235. And the ionized 235 can then be collected with an electric or magnetic field. And in theory, Avlis plants have a lot of advantages. They would be smaller and consume significantly less energy than centrifuge plants that produce similar amounts of fissile material. And this could lower the cost of enriched uranium. But it could also make these plants more difficult to detect through conventional means, since both their physical and electricity footprints are much smaller. And so we hope to develop signatures that demonstrate when Avlis is being used. So this diagram shows a simplified version of the Avlis process. And as you can see on the right, the vaporized uranium streams from this crucible where it's vaporized using an electron beam. It then passes through this tuned laser, and the ionized uranium is collected on a charge plate. And so developing valid signatures for Avlis should allow for the detection of a possible uranium enrichment pathway. And this is relevant because per the NNSA mission statement, quote, developing and maintaining the technical means to monitor whether the terms of a nuclear arms control treaty or other international agreement are fulfilled is a critical factor in ensuring that such agreements are successful. And so non-proliferation organizations need to have the ability to monitor for laser enrichment plants as well as conventional enrichment plants. And one way to potentially detect the existence of a laser enrichment plant is to analyze the product, the enriched uranium. So as discussed, this works by selectively ionizing U-235, taking advantage of a very small difference in the ionization frequencies of uranium-235 and uranium-238. So the laser has to be tuned quite precisely, but when it is tuned precisely enough, it attains essentially perfect selectivity. So a uranium vapor that passes through a laser beam will see all uranium-235 atoms which pass through the beam ionized, while none of the uranium-238 or 234 are ionized. And so some of the uranium-235 will pass through the beam, it will be ionized, and will be collected onto a charged plate, negatively biased, along with some of the natural uranium that does not pass through the laser. And so the system is designed with a specific enrichment factor in mind, such as 5% for a reactor or 90% or greater for weapons. And the geometry of the system is designed to take into account this mixing of the enriched stream with the pollution stream to attain the desired enrichment level. And so, as you know, the isotopic composition of natural uranium is approximately 99.28% uranium-238, 0.71% 235, and 0.0054% U-234. And now normally we wouldn't care particularly about the concentration of uranium-234, but in this case, it actually turns out to be a very useful marker. So to find the expected composition of the final product, we solve a simple system of equations involving the feed from the enriched stream and from the natural unenriched uranium stream. And we solve that combination to determine the expected isotopic composition. And so solving these equations with plugging in the desired value of enrichment, whether that's 5% or 90% or anything in between, can give us the expected proportion of uranium-234 that we'll find in the sample. And it turns out that for a 5% enriched product, we find that it's about 0.0052%, slightly lower than the naturally occurring amount. And for 90%, it's actually much lower, 0.00054%. And now this is in contrast to uranium enriched by gas centrifuge or diffusion, a mass-based process, because these mass-based processes select for lighter elements, and so they actually significantly enrich 234 to a greater factor than even 235. And so as a result, if we do a spectroscopic analysis of an enriched uranium sample, it's possible to determine whether the sample was enriched through AVLIS or through conventional means based on the percentage of the sample composed of uranium-234. And so a measurement of approximately 0.0052%, slightly lower than naturally occurring, this would be for a 5% enriched sample, would indicate the use of AVLIS. And then you would see something even much lower than that for samples enriched to higher levels of uranium-235. While in uranium enriched with a centrifuge or through diffusion, we'll actually see levels of uranium-234 higher than 0.0054%. And so this work should allow researchers to analyze a sample of enriched uranium and determine whether it was enriched with AVLIS. And further work that we're going to undertake will hopefully allow researchers to determine the sample's provenance more precisely, because differing designs can cause slightly different amounts of these trace isotopes that aren't really controlled for because they're not what people are trying to enrich. And so the geometry of different systems can potentially lead to different amounts of these isotopes. And so we're hoping to create a much more precise model based on the geometry of some of these existing systems that will allow us to determine not only whether AVLIS was used, but which precise design of an AVLIS machine was used. MTV has had a big impact on this project. It's given us the opportunity to connect with AVLIS researchers at Lawrence Livermore. And this work and the continuation of the model is going to continue over this summer in collaboration with LLNL, thanks to an MTV-funded internship. And this effort is going to be led by Chris Carson, who began work on AVLIS at LLNL in 1988 and has decades of experience in non-proliferation work. So in conclusion, this analysis of AVLIS, though only in its preliminary stages, will aid the NNSA in its non-proliferation efforts by providing novel means by which the provenance of enriched uranium may be ascertained. And the extension to analysis of different AVLIS configurations planned for this summer will result in a refined model capable of determining a uranium sample's origin with enhanced precision. Thank you.
All righty. Well, thank you very much for Henry for your talk. It was interesting. A question came from Professor Hayes, who wants to know, are there any experimental data to test or benchmark your model?
So that is one of the benefits of working with Lawrence Livermore over the summer, because since they developed this great AVLIS program through the 90s, they do have some of this experimental data to help back it up. And there are also some good papers out of India, which is looking at AVLIS as a means of recycling fuel for their thorium cycle. that does give us some experimental data to use.
Okay, that's interesting. Is Avalos used anywhere in the world on a routine basis, commercially?
Yeah, so I believe Avlos is used in Russia and South Korea for for industrial purposes and for the purposes of medical isotopes, but it is not currently used as a commercial uranium enrichment process.
Okay. But it does have you mentioned it consumes less power per unit mass,
Yes.
per unit mass of product,
Mm-hmm.
and it's a much more compact design as well.
Yes, and as opposed to a centrifuge, which could require multiple passes to enrich to the desired state, an Avlos machine could theoretically be designed to be so efficient that you would only need a single pass of your product through to reach the desired concentration of uranium-235.
Now, just a dumb question, I apologize. I would think 100% of the U-235 goes through because that's all that gets ionized, right? And you're using an electric field to pull out whatever gets ionized.
Mm-hmm.
Why does some of the product come through as well? Why does some of the feed come through as well that's not ionized?
Yeah, so this is a function of the laser beam diameter. If the beam is not as wide as the chamber through which the vapor is passing, then some of it just won't go through the beam and it will never be ionized.
Sure, that would give me less U-235. But you say, it seems to me you could have 100, the only thing I collect is U-235. But I got the impression from your talk that there was other material as well that came through.
Yes, so other material that is not ionized streams along with the uranium-235 and can be collected as well. And typically, you don't want 100% pure uranium-235 for any application. And so the system is actually designed to take advantage of that. You want your pure uranium-235 mixed with this pollution stream, the unionized feed, in order to obtain the desired level of uranium-235.
Okay, so you could, in principle, have 100% U-235 and then downblend it later. But what you're
Yes.
doing is downblending it in the process itself.
Mm-hmm.
Okay. Any other questions for, can you discuss the prominence of Avalos in the global enrichment landscape? I think he answered that. And somebody says, not in South Korea, from my understanding. Do you have any response to that?
Oh, sorry, I suppose I may be mistaken. Last I heard, they were still using it in some limited applications, not for uranium enrichment.
Okay. Yeah, it's something you might want to double check.
Yes.
They could have an equally valid application for another field as well. Okay. It's a little bit like libs in some sense, isn't it?
Oh, sorry, like what?
Does it have a relationship to libs, laser ionization breakdown spectrometry?
Sorry, I'm not familiar with that.
Okay. All right. There's just a little bit of there might be a little bit of crosstalk between the fields.
Mm-hmm.
I want to just take a peek at that.
Okay, thank you.
Yeah. Any other questions for our speaker, Henry? Okay. Well, then I'm going to close off this session. Thank you to all the speakers. We're going to have a break until 3:20, but I would note it's amazing to me how many of these students are working on machine learning. And I wonder if we're eventually going to get to the point where we are actually admitting the machine learning algorithms as our graduate students, and we'll then be able to give fellowships to the machine learning algorithms because they're so smart and they're learning. We'll have to wait and see if that's a part of the evolutionary process. Any comments from Sarah before we take a break?